This is Chapter 9, Video 4. In this video, we're primarily going to talk about how to determine if a reaction mechanism is going to be SN1 or SN2. We're also going to go over a little bit about how to control a reaction and force it one way or the other, either SN1 conditions or SN2 conditions. So just a couple of quick things before we get into that. We're going to look very quickly at benzylic and allylic halides. Now remember that benzylic halides are going to have a benzene ring and then a CH2, and then of course the alkyl halide. And allylic are going to be a double bond with a CH2 and then an alkyl halide. So interestingly, both of these types of substrates can undergo either SN2 or they can undergo SN1, and we'll talk about SN1 in just a minute. So you'll see here that both of these substrates are primary alkyl halides, so they can undergo SN2 reactions if you use the right conditions, and we'll go over what that is in just a minute. SN1 can also do this, interestingly, even though it's primary, when the alkyl chloride falls off, when the chlorine falls off and leaves a carbocation, you have a carbocation that is stabilized by the benzene ring. So if you wanted to, you could go and you could draw resonance structures. So I'll just very quickly draw one resonance structure here of this benzene ring, and I recommend that you practice and try to draw the rest on your own. But you can see that when we draw this resonance structure, what we've done is we've pushed the positive charge into the benzene ring. And so this is giving us some stabilization of that primary carbocation. So even though a primary carbocation normally cannot undergo SN1, when it's resonance stabilized like this, it actually can. And so you can see that situation down here again with the allylic substrate as well. So the bromine falls off. You have a primary carbocation. The resonance structure is drawn here. And either of those actually can react with the nucleophile, which is what they're showing kind of in this bottom example. So in this case, we have a situation where, depending on the resonance structure that gets attacked by the nucleophile, so the alkyl bromide is falling off, right? This is your heterolytic cleavage. You have a positive charge, a primary carbocation. But in the resonance form, if the electrons move, and I'll show how the electrons, of course, would move this way between the carbon-carbon double bond. In fact, let me draw that out really fast. So resonance would, here's how you would kind of draw your resonance structure. Sorry for the mess. The pen is not the cleanest way to do this. So here are the two resonance structures that you would draw out. This left one is the one indicated here, and this one on the bottom right is the one over here. And you can see that these resonance structures, either one, the nucleophile can attack, and so you can actually get two different products of this reaction. So now that we've kind of looked at these types of reactions, I just kind of said vaguely here SN1 conditions and SN2 conditions. Let's go over how we would make those reactions selective. So let's say you have this alkyl bromide here and you want it to undergo an SN2 reaction. Well, based on all of the factors that we talked about in the last video, you'd want a good nucleophile and a polar aprotic solvent. Okay, those are kind of the key factors here that you would like to include. So in this case, this is more of a SN2 reaction condition where you have a good nucleophile, hydroxide, probably coming from sodium hydroxide or potassium hydroxide. A solvent's not listed here, but we'd probably want to add a polar aprotic solvent like DMSO. That would be a good example. For SN1 conditions, you need typically a bad or weaker nucleophile. So water would do the same reaction, right? Hydroxide here is just replacing the bromine. Notice that you have the inversion of stereochemistry, whereas in the SN1 situation, the water is going to attack only after the bromine has left. So you're getting the mixture of stereoisomers here. In this case, you would use a polar product solvent. In the case of SN1 too, if you recall, the nucleophile is often the solvent, so water would probably just be our solvent. So then if we go back to the previous slide, and we wanted to do SN1 conditions, we'd use a poor nucleophile, like methanol, and that would also be our polar product solvent. And for benzylic and allylic halides that we want to undergo SN2 reactions, in these cases we'd use a good nucleophile. So in the top case, probably something like sodium methoxide, and the bottom one, something like sodium hydroxide. And we'd want to use a solvent that would promote SN2 reactions like DMSO, DMF, acetone. Those would all be good examples. Okay, so this is the situation where you're trying to do a reaction and you want to add reagents. And then let's also look about, hey, what happens when you're given a reaction? How would you determine the mechanism? So let's skip forward a little bit. And this is the strategy that you want to use if you are given a reaction and a set of conditions and you want to determine if the mechanism is going to be SN1 or SN2. So first you want to check and make sure you have a good leaving group. That's critical for both of these types of reactions. Next, you want to look at the substrate, because this makes it really easy in a lot of cases. If you have a tertiary alkyl bromide, for example, then the mechanism has to be SN1. If it's primary, and obviously not allylic or benzylic, then it has to be SN2. If it's allylic or benzylic or secondary, then we're going to have to look at the solvent, we're going to have to look at the nucleophile, and all of these kind of other conditions to see what's going on in terms of mechanism. So let's say you ended up with something that was secondary benzylic or allylic. You'd first want to look at the solvent, and if you have a polar aprotic solvent, you're probably going to be favoring SN2. Polar product solvents are going to favor SN1. And what we're going to do is we're going to just look at these factors and check each off and see which one is going to be promoted. Then you would look at the nucleophile. Good nucleophiles are going to favor SN2. Poor nucleophiles are going to favor SN1. And the last thing that you would want to look at would be concentration. So higher concentrations are going to favor SN2, and lower concentrations, meaning dilute reactions, are going to favor SN1. So hopefully, between these three factors, two or more, two or all three, are going to tell you, okay, SN2 or SN1, and you can make your determination that way to figure out what the mechanism is. So this is kind of another slide. This is basically the same information as the previous slide. It's just another table. So whatever way you prefer to kind of organize this information in your head. So this is giving you, in this table, the situation where you would have a poor nucleophile and a polar product solvent. And you can see that methyl substrates wouldn't react under these conditions. Primary substrates would not react under these conditions. If you had a primary benzylic or allylic substrate, then you would see a SN1 mechanism. And that's true also for secondary and tertiary substrates. Remember that sp2 or sp hybridized carbons are not going to do anything under these conditions. If you have a good nucleophile in a polar aprotic solvent, you can have an SN2 reaction for methyl, primary benzylic or allylic, and secondary substrates. Tertiary substrates will not undergo either an SN2 mechanism in this case, and of course neither will sp2 or sp hybridized carbons. And you can see down here I've also summarized some examples of what poor nucleophiles are, right? These are going to be, things like water and alcohols. Good nucleophiles are going to be things that typically have a negative charge. So you can see methoxide, and you can see a negative NH2. Polar aprotic solvents, again, water, alcohols, and polar aprotic solvents are going to be things like DMSO, acetonitrile, DMF, acetone. So hopefully this table here and then the previous list will help you figure out what the mechanisms of these different types of reactions are. So we're going to do a couple clicker questions so that way you can try this out and see if you can do this on your own. So first, why don't you give this question a try? Be sure to look at the substrate, the solvent, and the nucleophile. Okay, hopefully you recognized that in this situation you're not going to have any reaction. What you have at the indicated carbon here is an sp2 hybridized carbon. So this cannot undergo either an SN1 or an SN2 reaction. If you mix this all together, everything's just going to sit there and nothing's going to happen. Okay, let's give another one a try. So why don't you pause the video and give this clicker question a try, and then we'll go over it. Hopefully you identified C as the correct answer. So when you're looking at this problem, notice that there is a good leaving group. That's a good sign, and we don't have to worry about sp2 or sp hybridized carbons. This is an sp3 hybridized carbon. We have a poor nucleophile and a polar protic solvent. So those conditions are going to favor SN1, which means that the leaving group is going to fall off. You're going to have a carbocation intermediate, and so the water can come in either from the top or from the bottom, and so you're going to end up with a mixture of stereochemistry at that stereocenter. Notice that there was another stereocenter over here in the molecule. That is going to be retained. Nothing is going to happen to it. All right, let's try another example. Go ahead and pause the video and see if you can figure this one out. Hopefully, with this one, you identified the correct answer as B. This is going to be an SN2 reaction because we have a strong nucleophile, methoxide. This is sodium methoxide. Remember that sodium is going to be ignored, right? So that's a spectator ion. DMSO is a polar aprotic solvent. So these conditions are going to favor SN2, which means the methoxide is going to attack from the front, and the leaving group is going to come off from the back, so you'll end up with B as your product for this reaction.